says please. Oh, okay, got it. Yes. Then that means we can get started. Floor is yours.
Yeah. Thank you, everyone. Thank you for joining us today. This is for the follow-up workshop, follow-up cluster workshop. We've had the open hardware around for a while now, and we're really happy to have our second workshop. Sorry that we can't do it in person because of obviously COVID. Before we throw to Jerry, I'd like to introduce Jerry myself. Jerry DeVos has now started officially as the newest and first research hardware engineer. So round of applause for him. Another important announcement is that Jerry was recently announced as the 2021 Dyson Sustainability Awards winners, an international award that Jerry has won for his plastic scanner. So we are extremely proud of what Jerry's achieved, and also extremely happy that he's chosen to join us as a research hardware engineer. And I think he's going to be absolutely brilliant. So for the introduction and before throwing it to Dennis, I will let Jerry take over.
Yeah, thanks so much, Santosh. And yeah, actually this week was rather busy because I both started here as a research hardware engineer, and the announcement was made that I had won the sustainability award. So yeah, very happy with that. And I made a very short presentation for what the plan is for today. Apparently no Raspberry Pis 4 because they're not in stock, but this presentation, you should now all be able to see the screen. And yeah, just like last time, this workshop is also sort of a collaboration between not only us, but also the people from the DHPC and the Digital Competence Center. So yeah, very happy to do these collaborations and do some nice workshops together. Basically, yeah, I just quickly wanted to tell you a bit about the Delft Open Hardware and some plans we have coming up for next year, which, yeah, I will start working on and then be rolling out to you guys. And then we can continue on the main focus of today, cluster computing. So yeah, about 2 years ago already, we started this whole Delft Open Hardware because we want to allow students and researchers to work and make their projects open source and share them in a way that benefits both them but also the world. Yeah, just basically like my plastic scanner project. It was my graduation project, but I was able to also share it open source online so that people can chip in, and yeah, we can work towards better plastic scanning. So yeah, I'm happy to be able to also teach others to how to do this, and also have them known about like licenses, what works, what doesn't work, what's important for you, and yeah, hopefully work on some cool projects that try to solve problems. And maybe it's just a problem that you need to have fixed, and that's already great because other people will online find the same problem and they will run into your solution. And sometimes it can be very big problems where we need many solutions in order to combat these global problems. So yeah, the plan is for next year that we will host more events. We do some presentations with also guest speakers telling about other open source projects. We're also going to do a lot of workshops. We need to see with the COVID restrictions whether they will be more focused online, and then you can think about PCB making, 3D modeling, these kind of things, or whether we can do it actually physical and maybe, yeah, work on new hardware projects, do some environmental sensing or these kind of things. So yeah, we will keep you up to date on the Telegram channel that we have, and we will also work on a more up-to-date website. And yeah, from the beginning of next year on, we will also have like open office hours where people can come with questions, whether it's about licensing or whether it's about what is the right platform to share your project. So and then I will be helping you with that. So yeah, if you have problems or if you have questions yourself or you know anybody who has questions on these topics, then I'm here to help. And yeah, talking about workshops, in the end of September, we did our first cluster computing workshop. We assembled the Raspberry Pi with the Pi Zeros on top, and you could see, yeah, the different nodes and how they communicate. You can turn them on, you see some lights blinking, and you can access the different Pis and start running tasks. So this was a lot of fun. Everybody was very happy to work on this workshop. And also everybody wanted to have another workshop and going more in depth. So that was super cool to hear. And initially the plan was to do, yeah, all the playing and hacking and working on it here physically today at the orange room in the library. Unfortunately, that's not possible. So today, Dennis will give more of a presentation about also the history of cluster computing and more practical things. And then later at some point, we will be able to host workshops here again, and we can actually work on the Raspberry Pi cluster again. So yeah, I'm very happy about that. And I think basically now the floor is for Dennis, so I will stop sharing my screen. I will put the links to the notes in the chat of the Zoom, and then from there on, it's yours, Dennis.
Thank you, Jerry. Let me try to share my screen, because I would like to also make some of my other windows visible, not just the presentation, but let's see how that works. Screen, I can show the entire screen, right?
Yeah, you see.
Okay. But this way you also see all your faces again.
No, we just see your screen.
Okay, what do you see? You see two terminal windows.
Yes. And we see Perl Portable and some.
Excellent. Perl Portable is very important, but not today. Great. Then and now you should see my presentation.
Yes, that's correct.
Excellent. The last test. Let me do something as the last test. The last test, now you see two terminal windows and a kind of little presentation on the right. Yes, excellent. Okay, then everything is working. I'll start with the big presentation. Hi, everyone. As Jerry mentioned, this is a part 2 of our Raspberry Pi tutorial. Last time we actually assembled them and made sure that the hardware can talk to each other with some software that we installed. And today we'll try to recap what we did and start actually running things on it in parallel, and see how far we can get. I think that Jerry already posted a link to the notes. Otherwise, the link will be on the first couple of slides. So, recap. Last time, which was, when was it? Anyone remembers? It was sometime in October.
October 1st.
1st of October. It's been a while. So we built a Raspberry Pi cluster, which looked roughly like you can see on the slide. It had a Raspberry Pi 3 as a master node. And on top of that, there was a cluster head, which is a little circuit board that would let connect 4 Pi Zeros on top of it as computational nodes and put them together in the network using the USB interface. And this way you could then connect them to a local network. That was mostly done by Angela and Jerry in a neat and organized way, as you can see on the picture. And finally, we installed the Slarm scheduler, which made a lot of people wondering about the purpose of life and things like that, as you see on this picture. But finally it was working, and so let's recap a little bit. What is a cluster and why do we bother? So obviously, cluster is a collection of computers, and why do we need one? We need one if either of the two statements are true. Either we have a lot of users who would like to have access to a lot of resources, or we have one user who is very greedy and wants to calculate a lot of stuff at the same time. And so we would like to combine a lot of CPU processors, GPU, graphical processors, a lot of memory, a lot of storage in one place. And then, especially if a multiple user situation is true, you would like some sort of software to make a queue of all the calculations that people want to do and assign computation time based on some sort of priority considerations. Because otherwise, users will start fighting each other, and we don't like that. So, as you might remember, and this is like a very general chart, how real cluster computers also are often assembled, including the ones at TU Delft campus. Typically, you sit at home comfortably or in your office, you SSH to some sort of login node. And from that login node, you can then access the actual computational nodes and the shared storage. Sometimes for security reasons, there is also an additional layer in between you and login nodes, which at TU Delft is called Bastion. Well, because of the security reasons, so that it is impossible to do some harmful things in one go. You need to authenticate twice. For our PIs, that wasn't the case, so we just SSH directly to the login node, which was a master node, and then we could access worker nodes via a scheduler Slarm from there. Parallel computing and cluster machines generally have a lot of history. People started to play with that in the 60s already, although in the 60s they didn't even have proper computers. And then as the time went by, everything became bigger and more powerful. First, people just assembled a lot of CPUs together. Then later, people started dealing with specialized hardware. There were like vector machines and whatnot. And these days, a typical cluster would have a lot of CPUs, a lot of GPUs as well, for things like artificial intelligence and image recognition, etc., etc. But also, these days, people are playing around with ARM type of processors. So the type of processors you would have in your mobile phone or indeed in a Raspberry Pi. So Fujitsu, the vendor that built a big machine here at TU Delft campus, actually is one of the few vendors who provide ARM clusters. So who knows, maybe our little innocent workshop is more relevant to modern day computing than you might think. And here I just have a collection of nice pictures, I guess. 1950, some really steampunk, I would say, looking machine, very slow. 80s, obviously already super duper stupid design from 80s and 90s. That was a NASA cluster. Still very slow. I'm pretty sure that you can buy a laptop that is comparable today, or even faster, I would imagine, than this. 1998, more something like modern system, a lot of stacks with processors. Around that time, people realized that computing was becoming a commodity. And a lot of researchers actually ended up with, university kind of IT scrapyard with a lot of old computers, and people just started combining them together and just running things on them, which was not very energy efficient, I can imagine, but at least it worked. There were some early molecular dynamics simulation groups that were connecting Xboxes together, because it was a cheap way. Well, it was in America, so it was very cheap. And so it was the cheapest way you can get a lot of GPUs together. But what I would like to emphasize is that what we did last workshop, connecting these nodes together and installing Slarm, you could do at home with a couple of laptops. If you have a switch, You have Linux running on each laptop. You connect them all with Ethernet cables to the switch. You install Slarm on all of them. Here is your cluster. So it will not be the most efficient cluster in the world, but it will be a cluster nonetheless. Yeah, this is a more modern systems. There's basically, they are very boring, to be honest, to visit them, because you go there and it is a huge hall, like a huge garage with lots of cabinets with computers, very noisy. That's all you see. Well, if people have a lot of money, such as people in China, then you maybe employ some designers to make them look a little bit better. Finally, a bit of an advertisement. So you might have heard that Delft University is now building a new computer. An official name of the new computer was revealed last week, and it will be called Delft Blue, which of course is not the most original of names I've ever heard, especially in Delft. And it is very confusing to me personally, because Fujitsu is building it. But I have a lot of history of naming their computers something or the other blue. Deep Blue, I think, was one of their big machines, etc. So I hope that people will still be able to recognize that this is our machine. But so it will be available for general public, well, general public being TU Delft users from January. And it will be a very powerful machine. It is approximately number 250 in top 500. It's not too bad at all. And so anyone is very welcome to apply for some time on this machine. It will be generally available for everyone to log in and to see what is available. But then if you actually want to run stuff, you will need to apply for a proper account, which will be free. Okay, so end of the ads. Computers, we need a scheduler, right? So again, a recap from last time, a scheduler is a thing that makes list of all the jobs that people want to run and assign priorities to them. So here is an example of a typical queue on a one of the big academic machines. You typically have a lot of users waiting. So all these jobs, for example, are not running, they're all waiting. And in the last two columns, you can see how many nodes and how many CPUs people request. And the typical size of, oh, I want 12 nodes, 20 nodes, so like a couple of hundred CPUs. But you could also see one guy towards the end who requested 100 nodes with 1,200 CPUs. You know, easy peasy. If you have a big enough machine, you can do that, of course. So how do you work with cluster? We also touched upon that last time. You prepare, typically it's all remote. You don't have GUI interfaces typically, although there are options. You prepare your input files in terms of text. Those are basically script files that tell the machine which executables to run, where, how many CPUs, and you submit this job to the queue, and then queue does everything else. And we looked upon some typical commands. So this is a typical example of a submission script. You, at the top of the submission script, you have this kind of technical commands, starting with as batch, that is just for the scheduler to understand on which partition to run your job, in which queue, if there are multiple queues, how much time do you request, how many CPUs do you request, how much memory you request, etc., etc. And then towards the end of the script, you just say basically, oh, I want to run MATLAB, and as an input, I want that particular script. So this is what you do. This is a very typical submission script. And there are a couple of typical commands that you would like to remember for your future work with a real cluster machine. As batch is a command that submits a job script to the queue. Sq is the command that shows you the queue. We're going to use all of them today. Scancel is a very useful command when you actually want to cancel your job in the queue. Yeah, so what we did last time, we assembled the Raspberry Pi cluster, we set up an SSH connection to it, we set up a shared network folder, we installed the Slarm and the authentication daemon that would enable communication between the nodes. And we sort of checked that everything is correct. Some of you actually did manage to run a couple of times. So now I will try to show you the terminals. Now you should be seeing two terminals and my kind of a fraction of my slide. Is that correct?
Yeah, that's correct.
Perfect. So let's recap. So now I am connected to my Raspberry Pi, which is in my office. It has 4 nodes, 4 Raspberry Pi zeros, and if I issue a command sinfo, it will give me some information about what I might be seeing there. And so what I see there is one partition called my cluster. It is up. It has 5 nodes. They're all idle, so they're up and waiting for jobs. And their names is, the one is called CNAT. This is my master node, and you can see that I am also logged in on it. And then there are 4 compute nodes, P1, P2, P3, and P4. Another useful command is scontrol, and you can either show nodes or show partitions. So we can try with start with partitions. Scontrol, I am unable to type anymore. Show partitions, and here you can see it returns one partition named my cluster, again with all the same information pretty much. Here you can see that indeed I have 5 nodes, and here the total CPU, that is interesting, total CPUs is 6, and the reason being that my master node has 2 CPUs allocated to the cluster, and each of the compute nodes has 1 CPU in them, so I have 2 plus 4, 6 CPUs in total. And like I mentioned, they are kind of heterogeneous. The 4 Raspberry Pi zeros and sort of half of Raspberry Pi 3. So if I type scontrol show nodes, it actually gives me a list of nodes that I have. So the first one is my Raspberry Pi 3 with a fancy ARM version 7.1 architecture. It has 2 CPUs. Well, in fact, it has 4 CPUs, but 2 CPUs are allocated to a cluster. And then there is a whole bunch of technical information there. And then if I scroll down a little bit, I will see nodes from P1 to P4, slightly slower, older architecture, 1 CPU each. And they're all there for me waiting for jobs. And then we can also see one of the typical commands to run anything on a Slarm system is srun. And you can, for example, request, okay, Slarm, give me 5 nodes, any 5 nodes that you can find, and give me the names of those 5 nodes. And so I do srun nodes equals 5 host name. And indeed, it gave me all my 5 nodes. I don't have any other. If I can try nodes 2 and see what it gives me. Well, it gives me P1 and P2. I suspect that if you run it multiple times, it can actually give you different things. Now, very persistent, although sometimes P2 appears first. Interesting. It's very insistent on using this specific nodes. 3, yeah. I don't know. In principle, it doesn't have to be P1, P4. It could be twice CNAT and then something else, for example. But so those are the nodes. We can also check the tasks. So we can say, okay, Slarm, I want to run 6 tasks. What are my options? And then you run it and you see that, okay, it's suggested CNAT twice because it has 2 CPUs, and then each of the other nodes one time, because this way you can get 6 CPUs in total. Again, if we can check for smaller number, somehow it prefers the nodes first always. I don't know if Arco perhaps knows why that is the case. Feel free to jump in. But I think this is pretty much a random. Whatever talks back first gets displayed.
And what happens if you have more tasks than nodes?
If you let's try. That's a good question. And task 7, for example, and it says requested partition configuration is not available now. The job number 493 is queued and waiting for resources, which is a very misleading message, to be honest, because the message sounds as if they're just busy, and then whenever they're available, your job starts running. But in fact, this configuration is impossible on this particular machine, so it will never start running.
Yeah, in your case, it will happen never.
Exactly. Let's see if I do ask you in my other thing. Yeah, indeed, you can see that one job is scheduled, and it is just waiting. It will never start because I requested too many things. I don't know why it says that I requested for nodes, but it will never run. And then to illustrate, you can ask cancel from here 493. Yeah, now it's all released, and here you can see that the SRAM job has ended. So that is the recap of last time. So unfortunately, I will be the only one playing with the Raspberry Pi today. But at this point, we are mostly talking to Slarm. And so at this level of abstraction, to be honest, it doesn't really matter whether it is a Raspberry Pi or any other system. So you could try to reproduce all these tests on any HPC machine you can have access. But let's see. Right, funny jokes, of course. So that was the recap from yesterday, from the 1st of October. Today we're going to submit a couple of jobs, run things in parallel with MPI, which is a message passing interface, which is the program that actually parallelizes things. And we have one real science example to make the doggo happy. So if everyone is happy, we can start. Otherwise, if anyone has any comments or questions, please, now is the time to ask them.
Yeah, maybe a question.
Yes, please.
You showed indeed showing that you can run multiple things like the hostname command and such. It somehow assumes that you already have this all installed on the nodes and that the configuration of these nodes all is similar. But if you make your own software, then you should distribute it first. Is Slarm then also the way to go to distribute this? Because you can say, okay, I want to do these things on all nodes, so it's like a task. Or are there better ways to do that?
Well, if I understand your question, your question is if you have your own software, how do you make sure that it uses all available resources? Is that the question?
How to put your own software on all the cluster nodes, basically, if it's not installed directly on the system already. You should
right.
The hostname command, right? That is normally there. But if you have something else that you made yourself, then
right. So I think that after we run a couple of examples, you kind of see exactly that. But basically, if you compiled your code with MPI library that actually allows it to run in parallel on several CPUs, then your submission script just tells the machine how many resources, how many CPUs do you want to use. And then your program doesn't need to know which nodes there are. This is the job of a scheduler. This is the beauty of it. So you just say, okay, my code is compiled with a parallelization in it. It is capable of running on multiple CPUs. And I just tell the machine via the Slarm submission script, I tell them, look, just give me 100 CPUs and run this thing on them. And this is what it does. And then your program doesn't need to know anything specifically about the machine. Well, it has to be compiled on this machine to make sure that all the libraries are there and etc. But it doesn't need to know anything about the configuration of the machine as such. But we'll see that in a couple of examples. I hope that will explain it a little bit more. Any more questions? Well, if you come up with anything, just write it in chat. Jerry, can I ask you to sort of keep an eye on the chat, because I don't have enough monitors on me.
Yes, I'm keeping an eye out on the chat, and so far there haven't been any questions.
Great. Okay, so the first simplest example possible. This is still not answering Martin's question really, but this is again illustrating just the general concept of scheduler. So we are going to write a little hello world program that basically does the following. It asks the Slarm to schedule 6 tasks on a partition my cluster. It makes sure that the directory is changed to the current directory where you actually are. Then it says hello world, prints it to the file. Then it says, oh, the following nodes are reporting for duty, or rather in this case, I think the following CPUs will be reporting for duty. And then it run one of our previous commands, srun hostname, and just dumps them into a file. So basically, but this is not any software running in parallel really as such, but this is a real script that illustrates how Slarm communicates with nodes. So a question: what would you expect as a result of this calculation? So it dumps everything in hello world.txt. What would you expect in it after we run this? Well, let me rephrase. How many lines would you expect in your out file? Sorry?
One, just a random one that happened to run last.
That would be the correct answer if we would be rewriting the hello world txt all the time. But here I use this double. What's this characters? The character to the
double
right.
Quotes.
Double.
No. Greater sign.
Sorry, which sign?
Greater sign.
Greater sign. Yes. So if you just say one greater sign, then it rewrites the file. If you use 2 greater signs, it appends to the file. So instead of 1 line, you would expect multiple lines. And so how many lines would you expect then?
6.
Right, you would expect 6 files with your host, 6 lines with your hostname. But also before that, you would have 2 more lines saying hello world and the following nodes are reporting for duty, because we're just writing them. And then 1 more line saying have a great day. So you should have, if you do as batch hello world.sh, you should do something, you should see something like you now see on this. Let's test it. And never trust a chemist telling you about computers. So let's test it. For that, I need to actually go to my examples. And also, one of the things we did last time, we created a shared folder. So shared folder called cluster, shared folder. And in there, I already created a bunch of examples. So example number 1, hello world. There I have just 1 file. Let's open it, see how it looks like. Here it is. So basically, just the submission script that you've seen before. Now we're going to submit it and monitor the queue. So you remember that you could use sq as a command to see the queue, but now the queue is empty. What we wanted instead, we want to monitor it. So there is a command watch, and you can do watch sq, and then it just keeps the queue open all the time and updates it. However, often it updates it once a second, maybe, or something. And so what I expect to happen now is that we submit, the queue will be populated for a second because it will be done really quickly. We're not calculating anything, we're just writing the output. And then it disappears, and then we have a new file called hello world txt in a folder. So let's do that. As batch hello world sh. Ooh, I see something in the queue. You guys saw it? There was something in the queue for a split second. And now it's done. It created two files, actually. The first file it created is called Slarm output. In our case, chances are it is empty. Yes, because it will either write the output there if the output is not specified, but in our case, we did specify where to write, or it would write all sorts of error messages. But our calculation finished correctly. There was no error messages, so this file just stays empty, which is fine. And if we open hello world.txt, what do we see? We see the expected 9 lines, actually, right? The 6 lines of nodes reporting, again, twice from the master node and 4 times otherwise. And the other 3 lines that we just happen to write there ourselves. So that example already kind of gives you a little bit of an understanding of what the submission script does generally. It asks Slarm for resource. Again, like to a certain degree, that already answers Martin's question, because our little program that just wants to write something to the hello world.txt file doesn't know anything about how many CPUs there are. The program that does, the command that does know that is srun. And that sources the information from the Slarm about how many tasks on which partition, blah, 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 and then it just runs whatever command we want to run together with. Okay, a slightly more complicated example, but also not yet MPI related, just Slarm related and parallel execution related. So there is this programming language called R, a very pirate-driven language, apparently, which is designed for all sorts of statistical purposes. In this little script, which I just copy-pasted shamelessly from somewhere, what it creates a normal distribution plot. So a thing that looks roughly like this. It just produces a lot of numbers that are normally distributed. What we're trying to do with that is we're trying to use Slarm to actually schedule jobs for us. So we're trying to mimic this. So the previous example mimicked the situation of we would like to run one big fat job on all the CPUs. This thing will mimic the other example, is the other example of having multiple users. So what if each user wants to run one of those calculations, making a normal plot, but we have 50 users and they all are fighting for the same resources? What do we do then? So we can make a submission script like this. In this submission script, we only request one node and one task per node. So effectively, we request one CPU per job, which is not something HPC people like when you do, but this illustrates our point. And then what we do, we change the directory to a current directory. We create a subdirectory called plots, where we're going to dump all the distribution pictures, and we run this R program with some commands, and we are going to name each plot file with plot 1, plot 2, plot 3, etc., according to the task ID that Slarm generates. Again, the R itself, the program R, doesn't know anything about the configuration of the cluster, but the Slarm will help it to do it. So, and then we are going to run a command like this as batch, a submission script, but we are going to have one more option in our command that actually generates an array of 50 jobs and submits them into the queue one by one. Let's see what happens, because remember, we only have 6 CPUs, which means that only 6 jobs can run at the same time. All the others will need to wait. And let's see if Slarm is smart enough to arrange that for us. So we go back to our example. And let's check that I'm not bullshitting you. Generate R is just a little script with a couple of lines telling R how to generate a normal distribution and save it as a JPEG file. And another file here is rsubmits.sh, which asks for one node, 1 CPU per node on a partition my cluster in the current directory. It creates a subdirectory plots, and it runs the R command. Okay, now we need to submit it with as batch array equals 1 to 50 R submit. Okay, and we monitor the queue. The queue is the most interesting part here. So you see 6 jobs are being executed, and on the top you see the actual queue, all the other jobs waiting. So jobs 11 to 50 are waiting, while jobs 1, 2, 3, 4, 9, and 10 are running on 6 CPUs. One other interesting thing to notice here is that we have 2 CPUs from a master node from Raspberry Pi 3 called CNET, and they're much faster. If you now start, so now all 6 just started recently. So see how long it takes CNET to actually calculate this job, both of these jobs. It was less than 10 seconds. It was like 9 seconds or something. While P1, P2, P3, and P4 are still calculating. It is 20 seconds and they're still calculating. Let's see how long it takes. $31. This is bloody slow. 35. Yeah, about 35 seconds versus about 9 seconds. So this is how much slower the Raspberry Pi Zeros are compared to Raspberry Pi 3. But again, a program does not know anything. So Slarm just assigns random CPUs to a program. If you get to the fast CPU, good luck. If you get to a slow CPU, bad luck. But the program does not know anything about it. Okay, we are almost there. Only 8 last jobs are now queuing. 6 last jobs, 5 last jobs.
And
And see,
do
yes.
I understand correctly that this R script, it resides in the shared folder, and that's why all the computing nodes can access the R script?
Yes, that is correct. So typically in a real HPC machine, the folder in which you're working, typically it's either your home directory or your so-called scratch folder, where all the data is accessible by all the nodes. You start a job from there, and then you have only one copy of your script, only one copy of your executable somewhere, and then all the nodes can access these things. But they all know about the existence of each other. So they when they write the output, for example, in the log file, they don't overwrite each other. Unless you specifically requested them.
Okay. Yeah.
Okay, now you see that the queue is absolutely empty. Everything is done. Now we can see what files were generated as a result of that. Lots of Slarm output files. I suspect they're all empty because there was nothing there. But let's test. Ah, no, they're actually not. They cannot create directory plots. Aha, right. So the first time the directory plot was created, for whatever reason, the script keeps on remaking them. This is weird, but okay. In any case, once it was created once, everything is fine. And then it says that we are running R, and then it outputs a script. And then it complains about something. So error message. I'm not an expert in R, so I don't know. It is a warning message anyway. Typically, warnings are not crucial. If they say error, this is much more dangerous. Warning, whatever, you should take a look at them, see that there is nothing critical. I don't think there is anything critical. And it generated plots, so folder called plots. And in the plots, there's a lot of JPEG files, and we can take a look at them. So the SSH manager that I'm using is called Bitwise SSH client. It comes with a neat file manager as well. And so I can always just go to our example. That was example number 2. See all these files again. I can go to plots, all the JPEG files, and I can click on any of them. Here are standard normal distribution. I can click on any other. They all look very similar. They're not identical, but they are very similar. In a real HPC setting, so for example, if you actually generate some data that are important for you, you would like them to transfer this data back to your computer. So again, you can use this file manager. For example, I can click on plots here and download everything to my own local machine. And then I can open a directory to which I copied it, see plots, and see a lot of plots, just normal. So I can calculated that remotely in the other room on a Pi, and now I have all the files on my folder on my stupid Windows machine. So, you know, easy peasy. All right. Now, that were the first 2 small examples, after which I would like to make a little MPI theory intermezzo, and then run a couple of MPI examples. But it's been already 1 hour, so I suggest maybe we can take 5-10 minutes break. What do you guys think? We get a cup of coffee, go to the bathroom, and then we're back. We'll be fighting MPI together.
Yeah, I think that's a very good idea. And
anything in the chat, meanwhile?
There was a little question on why Raspberry Pi has 2 nodes, 2 available.
2 CPUs. So the answer to that is actually it has 4. But if you, so our master node also works as basically communication node, as a server. So if you allocate all 4 of them to the compute nodes, the server will be clogged up all the time. So typically on a real HPC, your kind of login server nodes are separate from your compute nodes, specifically for that reason, so that the compute nodes are computing and your login server node is just serving. But we only have 1, so we kind of split it in half and allocated 2 to the computing nodes and kept 2 as a servers. Yeah, does that answer this question?
Yes, it answered the question.
Okay, cool.
I would suggest starting again at 2.
Yeah, okay, 6 minutes break. Let's start at 2, and then we do the MPA.
Awesome.
Cool. All right, it's 2 p.m. Is everyone back? Probably not. Let's wait a minute or so longer. Santosh, I do not hear you. That's
Sorry,
better.
I think I said Jerry will be coming back soon, but I think the rest are almost back. But
Okay.
give it a
Yeah, let's just wait a second. If people can turn on the cameras to indicate that they are back, and then feel free to turn it off again, if you, for whatever reason, prefer that.
Or you can give us a reaction also, either way.
Yeah, or just, yeah, give a thumb up or something. Now we'll discuss a little bit what MPI stands for, and then have a couple of more examples. I guess I just start rambling, and then people will be joining. Okay, so far we didn't really use MPI for our 2 examples. It was just an example of either, well, basically both examples. We're doing something, some very simple serial task on a lot of CPUs. The difference was either we just requested 6 of them to begin with, or we requested 1 per task and then queued them together. But often what you actually want to do is you want to run 1 task everywhere. So for that, typically MPI is used, and MPI stands for Message Passing Interface. And it was designed in 1994, which makes me wonder what the all the parallel machines before that did. There was some older implementation, I believe, that people forgot already. And so basically, it is a bunch of commands and libraries that, if you compile them inside of your code, and then you write your code in a smart way, you can internally parallelize things. So, for example, certain mathematical operations could be parallelized. If you are summing up 2 matrices or something, you have to do it column per column and row, etc., etc. You can actually intrinsically parallelize it inside of your algorithm. So there are different implementations of MPI. 2 most popular are MPitch and OpenMPI. We are going to use OpenMPI, well, because it's open, although MPitch, I think, is also free. I'm not sure it's open, but it's free. But they do all very similar. The important part, of course, is to make some racist jokes, and this is what I'm going to do right now. The important part is to remember that there is no such thing as free lunch, right? So imagine you have 50 people building a bar. So like here's the example of Amish, because Amish people, as you probably know, are a particular type of people in America who reject all the modern things. So they are allowed to use a hammer and nails, but nothing electrical, etc., etc. And so when they build a barn, it is a good illustration of parallel work. So imagine 1 person builds a barn. Obviously, it takes, let's say, it takes 50 days. What if 50 people are building the same barn, do you think that they will be able to finish the barn in one day then? Any suggestions? Anyone? Tell me something. Somebody is writing in chat. No. Very, very eloquent. Yes. Yes. No. I would agree with Igor because all the parts of, sure, you can assign 50 different parts of barn to one person, but chances are that some parts of the barn depend on the other parts of the barn. So you cannot start building a roof before you build a foundation, for example. And so as far as parallelization is concerned, so this is the question that, yeah, if single Amish can build a barn in 50 days, then 50 Amish can build that barn in a single day. Well, not so easy. Because chances are that there are interdependent parts, and it actually takes longer because not because people are lazy, but because people will need to communicate between each other and wait until one of them finishes the job for the other to start. However, this is only one way of parallelizing. So you're parallelizing one task with many workers. However, you can equally parallelize many tasks with many workers. So if you have 50 barns to build and you have 50 people to build them, well, that will be 50 times faster. If one person builds their own barn, of course, it is not very fast, but it actually will scale linearly because of the fact that each worker is assigned one particular job and the other workers do not depend on it. And so in computational theory, those things are called strong or weak scaling. And there are obviously names of people assigned to that. And one is called Amdahl's law and the other one is called Gustafson's law. But the important thing is that, well, the first example was the example of so-called strong scaling. So the fixed total problem size with however many workers assigned to it. And the other one is called weak scaling with fixed problem size per worker. A little bit counterintuitive because I would argue that it is a very strongly scalable problem if you just assign multiple problems to multiple workers and then it scales linearly, but it is called weak scaling. And so the difference between strong scaling and weak scaling, of course, is the basically amount of communication that needs to be done between the workers. And there are a couple of also not always very intuitive exercises, so suppose you have a program into which processor 1 generates information and passes it to processor 2, and then processor 2 passes it to processor 3, and so on until the end. Suppose you have 5 processors, and you can only send or receive thing in one cycle of a processor. So then how much time would it take to pass the information from processor 1 to processor 5? The answer is in the slide, but anyone wants to explain that? People are shy today. It takes, yeah, yes.
Well, one node supposed to send message to each, well, node or processor.
Not to each, but to the nearest neighbor, let's say. So suppose, suppose each processor can only send or receive in one cycle.
Yeah, so it's essentially a sum of the number of links, right?
Right. It will be minus, well, a number of links, exactly, not number of processors. So if we have 5 processors, it would be 4 cycles because 1 to 2, 1, 2 to 3, 2, 3 to 4, 3, 4 to 5, 4. So basically, although we have 5 processors, if data is traveling sequentially, it will still take a lot of time to pass it, because this is how this chain of communication is designed. What's even worse is that suppose you try to make a loop. So the first processor generates data, sends it to the second to the third, and so on and so forth. And then the last one is trying to communicate back to the first one, but the first one still tries to send new data out. But the processors can only do, in our supposed situation, can only do one action per cycle. They can only receive or only send. Then it will be the previous situation until processor number 5. And then the moment processor number 5 tries to send something to processor number 1, and the processor number 1 at the same time tries to send something to processor number 2, there will be a deadlock, because processor number 1 cannot receive and send at the same time. So sometimes processing, exchanging information is actually a lot of trouble. And so in this particular case, again, those are all mathematical sort of examples. Of course, you can argue that parallel programming doesn't work this way normally. You would have some sort of cache somewhere in between, or one of them will be in the middle communicating to all of them or something. But, you know, yes, Angela.
Yeah, but there is one more case. So if, let's say, number 3 will say, like, sorry, but I cannot now. I wait. You know,
right, sure,
you know,
sure.
busy, and so wait, and then the whole chain will wait for number 3 just to do something, you know.
Yes, of course, that would be an option. But you know, our little program definition doesn't have a wait statement in it. So this is just a maths example, right? And then there are other maths examples. So for example, you can try to solve this deadlock problem by assigning, by having an odd number, an even number of processors that is divided by 2, and you can say that, okay, the odd processors, for example, first send, then receive, and the even processors first receive, then send, and then everyone is waiting for everyone. It takes longer because basically, however many cycles you need to wait until you're done with generating data, receiving the data, and sending the data. But this way you avoid the deadlock. In any case, the important message here is that if you want to write a program which is truly parallel, you have to think about basically this, about the fact that it's not only the calculation that needs to be done, but also the communication that needs to be done. And therefore, MPI is not called parallel something. It is called message passing interface, because depending on how much information is exchanged, this is the most crucial step. That could be the most crucial step. So a lot of people, for example, try to employ a fancy parallel algorithms. And then they run it on their laptops, and then they say, oh, but I don't see any speed up. And this is just because the consumer grade CPUs, they don't have all that much sort of independent cache in them. And then it is the same amount of cache that is available to one CPU or to all CPUs in your multi-CPU processor, and then there is no speed up. Anyway. So just something to think about. Back to simple examples. Now we are trying to take a look at the same hello world kind of thing, but instead of asking the Slarm basically to assign one hello world statement to every CPU we requested. We request a number of CPUs, and inside of our program. This time it is written in C, because C is a very powerful language. It is also a very cryptic language, so at least for me. But basically what it does, it loads a couple of libraries. So stdio, it is standard input output, so it can read and write. MPI.h is the library that actually parallelizes things. So specifically it can use things like MPI ranks and things. And MPI ranks tells the program what is available there, out there. And then in this particular instance, it will source this ranks and then print hello world statements per rank. So it is basically very similar to our example number 1, except now it's not the Slarm that assigns all this stuff, but this is inside of the program. Although the Slarm will provide the requested number of CPUs to the program anyway. Of course, it is in C, so it is not an interpretable language. It is a language that needs to be compiled. So we will need to compile it, and you don't just use the GCC or whatever C compiler you have, but you need to specifically compile it with MPI. So there is a compiler called MPICC, for example, that compiles this thing. It will create our little program called a.out. We will need to run this a.out with a command called MPI run. And basically, again, what it will need to do, so the program itself is parallelized, right? As indicated here. So it is sourcing the whatever MPI ranks and then assigns them to however many print statements it does. However, it doesn't know, the program itself doesn't know how many CPUs will be thrown at it. So here Slarm comes into action. So we again ask for 6 CPUs from Slarm. We change the directory, we just print something, and then we run an MPI program that, based on these ranks, will be spitting out hello world message. And as a result of that, again, what would you expect? How many lines? How many anything would you expect? Anyone?
6?
Yes, well, at least 6 of statements from CPUs and perhaps master nodes on top of it, right? So it will first say what master node is, because this is independent of a program, and then we run the program, and then there will be 6 more lines. Okay, let's check if this is the case. We go back to our examples, and here I have 2 files, the C file and the submission script. The C file indeed just looks like that. We load 2 libraries, we source the MPI process rank, and we print the statement based on this rank. Okay, let's compile it. And we need MPICC. Hello, MPI. Something happened. Woohoo, we have a.out. And this is a binary. This is not a text anymore. And the sub MPISH, yeah, it asks for 6 CPUs, and then it does MPI run on our binary. Again, this is a good example back to the original question, is that the program is written in a parallel way, but the program doesn't know anything about our computer, and it doesn't know how many CPUs will be available to. This is the Slarm's job to assign this number, and then the program works with however many it got. Okay, let's try as batch sub. Again, check the other terminal window for the queue. Probably it will be very fast. Yeah. 3 seconds. And then we got 2 more files out. We got Slarm out, and we got 1 out. We only got Slarm out because in our C program, actually, there was nothing about where to write. It just says pretty much printf hello world. So they just print somewhere. And so by default, it prints in the terminal window, but because it's not an interactive thing, right? We just submitted a job and forgot about it. So it writes in the Slarm output file. So if we open a Slarm output file, we indeed see what we expected to see. The master node reported, and then all our 6 CPUs report. Please note that they are reporting in random order, pretty much, because whatever happens to be available is available. And so now we have 0, 1, 5, 2, 4, 3. And last time I ran it was some different sequence, which also makes sometimes programming in parallel a little bit more tricky, because in certain situations you need to keep track of which processes have which indexes, because you cannot, if you summing up 2 matrices or something, you cannot just assume, if you assigned each row or each column of the matrix to a CPU, you cannot assume that they will be reporting one after another. They might be reporting kind of in a random order. So then you will need to take into account which CPU is reporting and be able to figure out which one is that. But that's for more advanced MPI programming courses, which I am not qualified to give. All right, so that was a truly MPI program that took advantage of the MPI libraries, of the fancy programming inside of the code that interacts with MPI ranks, and of the Slarm scheduler to tell it how many CPUs it needs, etc. Another example, this is in C. C is a very typical language for MPI programming, but Python. Jerry, you have a question? I don't hear you.
Sorry. While explaining the previous example, the 2 questions came up.
Okay.
So one was from Maurits. I don't know if he wants to explain it himself, and one from Igor.
Sure.
Yeah, sure. I can
Go ahead.
So I was thinking about your Amish metaphor, and I was thinking,
Yes.
when at the moment that we're assigning 50 people to work on the bar, and a few of them would need to be working as project managers, so you might be losing some efficiency that way. And I was wondering whether the equivalent would also hold for HPC, or whether, because you have dedicated scheduling nodes, that would not hold, and the project managers, so to say, are already there, and you won't lose any efficiency when you're scaling up.
Right. It depends. For simple cases, yes, you would have a node from which you. So there are different levels of where the efficiency can be lost, right? So as far as the architecture of the cluster is concerned, there are dedicated nodes that deal with the loading of, communication between the nodes, as far as Slarm is concerned. So this is fine. But of course, depending on what your program does, if every individual nodes generate, in our case, they just spit out their ranks pretty much and nothing else. But if they would generate a lot of data that needs to be processed by some other nodes, then indeed your program needs to be written in a smart way. So maybe perhaps you get 6 threads, and then maybe you need to reassign what your program does in them. I can imagine an algorithm that in which 4 of the threads would generate the data and the other 2 will be analyzing the data. But I think it's up to your algorithm.
Yeah, thanks.
Can I make a little comment? So perhaps the thing is not only about the program itself, but about infrastructure. If your program is writing stuff to file which is on a shared folder, you're stuck in, your bottleneck is network interface, because you can be on a Wi-Fi worst case scenario, okay case scenario 1 gigabit Ethernet, best case scenario optical fiber.
Actually, the best case scenario would be InfiniBand, which is probably based on optical fiber. And the worst case scenario is what we are having. It is USB connected, USB 2 connected nodes. Fortunately,
I thought a lot of times Wi-Fi dongles, they're mostly made like Wi-Fi to USB. So actually it's the same bottleneck in terms of bandwidth.
I guess so. But this is a very good remark. So you might have heard like philosophical rant from me. You might have heard that some computers are referred to as supercomputers and some computers are referred to clusters. That has to do with like whether it is a completely sort of independent instances with their own memory, etc., or if it is a properly combined architecture where there is a lot of CPUs talking to the same cache, to the same memory, and etc., etc. And so most of the computers are kind of in modern days are clusters, and they need to like each node needs to talk to each other all the time. And so typically, like Igor mentioned, we have like Ethernet. You have a gigabit. Maybe like these days you can have like 2.5 gigabits or something, or like up to 10, I think, is more domestic. But so throughput is one thing, bandwidth is one thing, but the latency is another thing. Is how quickly it all responds to each other. And so a proper cluster computers are connected with InfiniBand cards, which have very, very high throughput and very, very low latency. And are very expensive. So basically this network interfaces and cables are sometimes more expensive than the computational nodes themselves. So yes, it all depends on everything. That is my stupid answer to this complex question. And there was a second question as well. Was there?
Yes, it was a question from me. So how to configure Slarm task file. So it takes one node and loads all CPUs on it, but only on that node.
Right. So we can go back to one of the previous examples, like here, for example. Right. You can have as batch nodes specified as one, and then you can have tasks per node or CPUs per node. There are different similar commands. You just need to Google that. So in your normal supercomputer HPC situation, each node obviously will have multiple CPUs. A typical number is 16, 32, 64, something like that. And then you can say, basically you can always, so this first as batch commands will tell how many to reserve, not necessarily how many to use. And you can say nodes 1, tasks per node or CPU per node maximum that you can have. This way you will block the whole node for this job. When your job starts running, it will occupy the entire node. And then depending on how you can always do MPI run or MPI exec or whatever with a lower number. If you were just interested in occupying all the memory on the node, for example, that would be a valid strategy to say, okay, I don't need 32 CPUs, but I need 256 gigs of RAM. So I occupy the entire node, and then on this node with a couple of CPUs, I run my memory heavy calculation, for example.
Okay.
Your system administrators might be not very happy with such a solution, but it is a solution.
Is there a way to get this number automatically or not?
How many CPUs you need? I am not ready to answer you that. Maybe there is, maybe there isn't. Some computers have very heterogeneous. They might be nodes with different CPUs. Maybe there is a command that retrieves the information. I'll need to Google that, and I'll be back to you after the work.
I just know there is like a command Slarm space -c, which provides you information about one particular node, but I don't know if it can be usable within script. So apparently there is a way to parse out this string output, but is it usable?
Yeah, I suspect that there is a way to do that automatically if you're very smart.
Okay.
But I'll try like Jerry, if you could write it down somewhere, this question, and then send all the unanswered questions to me, and I will try to address them later on.
Yes.
Meanwhile, if somebody does know the answer, please jump in.
Okay, thank you.
All right. So now what we're doing? We're doing Python. Right. So Python can also be parallelized, and there is a library called MPI4Py. Basically, that is equivalent of whatever we were doing with MPICC. It's of course Python is an interpretable language, so chances are it will be slower in many situations. But here was a little program that, again, I just copy pasted from somewhere because I'm not a software engineer, that calculates the number pi. So 3, 14, 15, etc. And it does so with Python, and it actually splits the job into however many processors you throw at it. So it happens somewhere here pretty much. If you then import MPI4Py, and if you then in your Python code, you can refer to again the ranks of your threads that you requested. So it is very similar. It just the syntax is a little bit more complex because this program is also a little bit more complex. And basically, again, the program doesn't know anything about the architecture of a machine or how many threads we are throwing at it. It just is ready to receive however many numbers of threads you threw at it. Blah, 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 some more Python. Whoever is interested, please go to my notes and get the original source code. And then what we do, we just say, again, Slarm, please give us 6 CPUs. We change the directory, and then we use this 6 CPUs to call Python, to call our calculate Python script. As a result, we should just have a number. So we as batch the submission script calls Python with MPI with 6 processors, which calls the calculate Py script, and then it spits out the number. Let's see what it does. The last time I ran it, it was not very good. It only calculated 3.1418, which I suspect is not a very good approximation. But let's see what we get here. Python MPI. Again, let's check calculate Py. So this is my program. We import MPI from MPI4Py, so we can address the ranks of threads, and then we calculate the pi, and in the end, yeah, we print out the message pi is approximately something for the other. And in our submission script, it is really very simple. We just ask Slarm to assign 6 CPUs, and then we run a Python with 6 CPUs. Let's see what happens. Again, monitoring the queue below. Subcode, right. Yeah, something, 6. I see the 6 CPUs, the 5 nodes. 6 seconds, 6 seconds, quite a long time, relatively speaking. Again, in our original code, the output file was not specified, so it is spitting out in the terminal. Therefore, in the Slarm output file. We open that. Woohoo! It is actually calculated. Again, 1418. I think our algorithm is really bad. So a homework assignment for whoever wants to fiddle with Python over the weekend. Try to rewrite this program such that it actually spits out a better pi approximation. Yeah, it also gives you the error, which is quite big. Well, such is life, I guess. Okay, so far, yeah, so far we did 4 examples. right? The first two examples were just without MPI, were just either requesting a lot of CPUs for the same job, but which inside of that job was kind of several serial jobs, or we just have a bunch of serial jobs and that we queue them all together with Slarm. And with MPI, we had two examples with C or with Python. Both of them were basically compiled with MPI library, and inside of the code, they were able to request the ranks of the threads that they were thrown at them. And then based on that, parallelize the calculation inside of the code. So now we are going to do the same, but with a real science example. I'm a chemist or a material scientist, chemist. So I found this little neat example with a tool called Atomic Simulation Environment. So Atomic Simulation Environment is a kind of a collection of Python scripts for manipulating atoms and optimizing the geometries, calculating the total energies, and all sorts of physical and chemical properties of materials. And one of the typical tasks in chemistry is if you investigate a reaction. So assume there is some sort of surface dynamics going on. There is aluminum surface, and on top of the aluminum surface, there is a gold atom. And this surface is not very flat, right? Like, because of the packing of aluminum atoms, it has different types of sides. It has kind of bumps and protrusions in the surface. And so imagine this gold atom is residing in one of the protrusions, in one of the depressions rather, and then goes over the barrier of things that are sticking out and then goes into the other hole in the surface. This process will be energetically demanding because you will need to add energy to the system to push this atom over the barrier. And in between these two minima, there will be the so-called saddle point. The saddle point is a point on your potential energy surface, so to say, where it's all relaxed in all directions except for one. And this is your reaction coordinates, where the atom wants to go. And there is this method called nudged elastic band method that lets you find this transition states. And so basically what it does, it initiates the system where there is like an initial configuration and the final configuration. And then it kind of makes an estimation of the path. So it just makes some sort of linear combination, what would be in between this initial and the final stages. And then it connects, it creates several kind of snapshots of this trajectory. So, okay, we have the initial, the final, let's approximate this pathway with a couple of intermediate steps. And then there is a smart physics going on. You kind of connect all the steps with a kind of springs so that they don't go all over the place, that they're kind of connected, they kind of stay in the same pathway, but they have some wiggle room to optimize themselves so that in the end, you get the optimal transition state. It will require energy to get there, but it will require the minimum possible amount of energy. And so, like, you can imagine that, for example, if you have some sort of isomer like this, and then you want to rotate it, there will be some sort of barrier in between, and then once it is rotated, it is fine again, such as illustrated on this picture. So basically, here are the initial trajectory that we are going to generate. So we have the initial situation of this. So the gold, so this is our unit cell, this little box. And you see that this gold atom here, it can kind of be in 4 different positions here. But we're interested in transition from this position to this position. So it kind of will roll over this barrier into the next site on the surface. And we need to first generate this structures, and then we need to calculate the possible trajectory between them. So let's start with generating the initial structures and taking a look at them as well, so that it's slightly less academic and a little bit more tangible. So we have this Python code called generate trajectory. This is basically a Python code that talks to all this atomic simulation libraries, and they know what different atoms are, they know what different types of surfaces are, and you just specify which ones you need, and it generates it for you, essentially. And it writes it in some sort of trajectory file. Oops. So we can do Python 3 generate trajectory and see what happens. It does something, and we see two new files, initial trajectory and final trajectory. And let's try to visualize them. We have here these two files. I will download it to my machine. And on my machine, I have a little tool which comes with atomic simulation environment, which is a GUI, which lets you open these things and see them. So I'm going File, Open, to my directory. So initial trajectory, for example, will look something like this. So this is our surface. And beneath our surface, beneath there are a couple of layers that are kind of fixed, and then this one top layer could be optimized, and then the gold atom could move from here to here. So this is just a one. I don't have a mouse here, unfortunately, so it's gonna look ugly, but basically this is one unit cell, and you can always do view repeat, I think is the thing. So if you, so for example, if you repeated them, translated this unit cells, now you have two unit cells next to each other. And so what we are trying to do is we're trying to move this gold atom to here, to this position. So this is our initial configuration. Let's see how the final configuration looks like. So again, in the same folder, we have another thing called final trajectory. Yeah, see, now it moved. So it was around here, and now it's moved here. And so what we are trying to do is we're trying to find a position in between. So somewhere around here, I would assume, that it will pass on the way, and that will be a transition state. And transition states are important in chemical processes because typically between the reactant and the product, the transition state will have some energy associated with it, some energy barrier, which you will need to overcome in order for this reaction to run at all. And this is a typical problem in catalysis, for example. You're trying to find a surface that makes certain moves of atoms as easy as possible. Okay, if you're not lost yet, so what we did, we ran this initial trajectory, we generated two files, and now we have another script, which is called neb.py, so nudge the elastic band.py, which actually optimizes, so it creates several snapshots in between, and then it optimizes them all in such a way that our pathway from initial to final is optimal. And then the highest point in this optimal trajectory is the transition state. And then we can read its energy, and that will be the energy barrier that we need to work. And so what it does here, it actually splits this pathway in several snapshots. And then it needs to optimize each snapshot. And this is exactly the point where parallelization could be very easily achieved, because you can just assign each snapshot to one processor, or each snapshot that would be the super easy way to parallelize. Of course, if your program is super smart, you can do each snapshot with multiple processors, but this is not important. And then we just, so this is what we do. We just request it to be parallelized over processors, and we run it with that many processors. Let's see. So again, we have this NEBPi, which is exactly that. It works with ranks as always, and based on the ranks, it assigns different snapshots to different processors. Again, an example of program that was actually written with parallelization in mind. And our submission script would be also very simple. It will just request 6 CPUs and will run Python on 6 CPUs. And we generated, remember, we generated the initial trajectory and the final trajectory, and our NEB Python code will read them somewhere. So it is in the code. Okay, so let's submit as batch sub NEB. Okay, let's see the queue. Yeah, the queue is doing something. There is a calculation going on. Yeah, 14 seconds. This is a real stuff, you know. This is real chemistry going on. So it will take some time. Hopefully, very short time, because it is still using relatively cheap force fields to calculate the interactions between the atoms. About 30 seconds already and still calculating. 32 seconds. Well, that's not too bad. Let's see what we got. We got several new files. We got a Slarm out file. Let's see what's in there. Yeah, here are all the energies of the transition state, I would imagine. So you can, those are energies in electron volts, probably, or something like that. And you can see that we were going for 17 optimization steps, and the energy was going down. So we started with 4.22 almost, and we ended up with 3.69, which is quite a bit smaller in chemistry terms. Still, this energy is very high compared to initial and final. So, but in real life, 3.6 probably will not happen. But we stopped. You see that the thing stopped calculating when it basically the next energy is very similar to the previous energy. So there is some sort of threshold that is translated into the force. And if the force is small enough, we stop, because we say that, okay, this is optimized. As far as we're concerned, this is optimized. And we got a new file called NEB trajectory. So let's see what's in it. NEB trajectory. Now we can open it again in our graphical user interface. Open NEB trajectory. Perfect. Let me try to zoom in. This is the final. This is the final. Final is the same as we saw before, and they did it multiple times because it was optimizing this thing 17 times as we saw. But you can see that. Let me maybe rotate it. So the gold atom will be moving. See, this is probably around the transition state, and that is the final state. So that is the final state. This is the original state, and somewhere in between there will be an optimum. And so it did it 17 times. So this looks like a stupid video, but the last one will probably be the most optimum. So this last 5 steps or so, 1, 2, 3, 4, 5. So that will probably be the true, well, the true transition state as far as our calculation is concerned. And so ASE also provides you with this nifty tool of generating PDF reports out of it. And so you can, yeah, you have this, now we analyzed our trajectory just by looking at it, but we can do it in a slightly more automatic way. And we can actually plot this plots. Trajectory. Let's see. If I typed everything correctly, it's going to do something. Yeah, it's doing something. It's processing 17 or 18. Probably it's 17 starting from 0, so it's 18 attempts actually. It will process them all, and it will generate a PDF file. And this PDF file we can open. Let's see. Yeah. Woohoo! That looks great. So basically, this is our initial state. This is our final state. We have some sorts of energies. And as we go, they actually go down as well. And so in the last one, we have, well, quite a low energy barrier. Probably in the original output, this 3.6 was not the delta, was something. Maybe it was the absolute energy. The delta now is the energy of the barrier is 0.4 eV, which is a very decent barrier for some sort of surface hopping process. But again, what you should remember from that is that that was an example of a program that was written with parallelization in mind. It knew what to do with the ranks of threads that were given to it, and then it parallelized the task based on the physics of the task. So here we have multiple snapshots of the trajectory, and each snapshot was sent to each individual CPU, and it was then calculated. The code did not know about how many threads will be available. That is the Slarm job. So there was a smart programming, MPI library, and a Slarm working together. All righty. Wrap up. That was the last example. So in these two workshops, we learned how to build a Raspberry Pi cluster, how to set up all the necessary software, and those of you who attended the previous one remember how many tears and sweat and blood it costed us to actually make the Slarm running. And then today, hopefully, I was able to illustrate that with a little bit of trickery and a little bit of smart programming, you can actually make use of this available infrastructure. It makes your life easier. Well, now, assuming that you also attend some MPI programming course from somebody who actually knows what they're talking about, then you will be fully prepared to whatever scientific life throws at you. Finally, these workshop notes are available on HackMD, so feel free to look through them. Those of you who are super interested, talk to Jerry, or me, or Jose, or Angela, or Moritz, or anyone. It should be possible for us to connect a couple of those pies that you assembled last time somewhere at the university network, so that people can access them. So if somebody is really interested, that could be organized. We were following some online tutorials that were already there. We were following some atomic simulation environment things. Feel free to check out the MPI for Python. This is all the rage these days. And there is an HPC intro software carpentry course, which also follows some very simple. Yeah, other than that, thank you for your attention. Let's see what kind of questions we have. Perhaps more chemical question rather than computational, but what is the criteria of optimality of way? there are two criteria for optimality of weight. So first criterion, it has to be a mathematically saddle point, which means that there are no forces acting on this atom except in one direction. Because in principle, if you try to mathematically optimize your geometry, that means that you have some sort of potential describing the interaction between the atoms and the positions of these atoms in space. And then you're trying to minimize the forces acting on atoms until they are below certain threshold. And so in a general situation, this forces acting on the atom will be three-dimensional. So the atom could be moving in any direction at all. But if you're talking about a true saddle point, that is the situation where there's only one way for atom to move between A and B. And so it has to be a real saddle point. That's one thing. And of course, we are optimizing the saddle point, and it is still a question of a minimization, energy minimization algorithm. So we assign a threshold. So if we optimize, then the new thing that we got is more stable in energy than the previous one by a large enough number, then we accept it. But if it is really very similar, then we just say we're done. We can't be bothered anymore. So as long as it is a true saddle point with optimized enough energy, that is the two criteria of optimality over weight.
Thank you.
However, of course, we started with the initial and the final, and we ran the first script just making some sort of estimate of it, and then we were optimizing this estimate, and we were actually never checking the first criterion of a true saddle point. That in chemistry you would need to run a vibrational analysis to see if all the vibrations are in the real domain and not in the imaginary. But I'm not going to go with that. But also there could be a situation that two local minima, the initial and the final state, could be connected with multiple pathways. And then you either have a really smart algorithm that can sample those, or you just say, okay, we just employ the chemical intuition to assume that this is how it goes, and then we optimize this guess. So it's all, there is never a guarantee that what you found is actually super duper smart. Therefore, in chemistry, I know this pains of being a theoretician in chemistry, because all the experimentalists are always asking this question, like, yeah, but what is the proof that you can calculate on your stupid computer anything stupid you stupid want? You know, and then you say, okay, then we want to calculate not just the energies and geometries, but also some sort of spectral characteristic that can be compared to the experimental results. And then if your calculation makes mathematical sense, and on top of that is kind of sort of resembles the real experiment, then everyone is happy. But this is a not very bulletproof criteria. This is a more psychological criteria. Yes.
Okay, thank you.
I think that were all the questions so far by everyone. If there's still more questions, then yeah, feel free to put them in the chat. And
hey Dennis, can
Yes.
I have a question?
Sure.
So for no matter what problem we are solving, if we want to take advantage of this class computing, do we have to code our problem in a parallel way? So I mean,
yes. If remember the Amish people building the barn. So you can parallelize your task in two ways. You can either make multiple independent tasks out of it. Then you don't need to know anything about MPI. You just need to be able to trivially assign multiple tasks to your problem. An example, again, chemistry, for example. If you try to optimize something, right? And you say that I would like you have a surface again, and you have an atom. and assume you have 50 different ways of where this atom can be on the surface, right? Now you have two options. Either you just sit down, create 50 initial configurations corresponding to these 50 positions of atom on surface, and then submit 50 independent jobs, each requesting one CPU, and then you will have 50 energies and 50 optimal geometries. And then again, you sit down and you're like, okay, based on this one is the best. And in principle, this will be a linear scaling in your parallelization, because your 50 jobs will be done at the same time, provided that they roughly take the same time to get, right? But this is not a parallel program. This program doesn't know anything. It's just that you reformulated your question such that you ran 50 parallel programs. However, you could also write a smart program that generates these 50 configurations by itself, then looks for this threads ranks, sources them, and then assigns each of these 50 to each rank, sends them out, and then calculates everything in one go, and then does the analysis in one go, and then gives it back to you, and it's done. This will be a better parallelization, although even that is technically speaking still running 50 different things. Even more smart way will be if you're really a skilled programmer and you can actually code the optimization algorithm itself to be parallel. Because optimization algorithm itself will deal with differential equations and integrals and whatnot, and other scary mathematical words. And some of the scary mathematical words can be parallelized, such as, you know, matrix A plus matrix B could be parallelized because each processor could take one column and one row and then combine them together. So the level of parallelization of your program depends on how deep you want to dive into that. But generally, yes, if you want your program to be truly parallel, you need to write it. You need to code it in a truly parallel way.
Thank you.
But I
Thank you so
think
much.
that most of the simulation software, be it chemistry or fluid dynamics or whatever you use in aerospace engineering, I don't know, like something. I think that most of the kind of commercial or industrial or academic codes, they can be parallelized already. They know this. So
Thank you so
a
much.
lot of optimization algorithms, a lot of numerical solvers, a lot of kind of mathematical libraries, they are intrinsically already, somebody wrote them in parallel.
Cool.
So depending on what you like, if you're interested in a real case, talk to me, because I am a data steward in this new Delft Blue supercomputer. So I will be able to, I'm not a mathematician myself, but at least I will be able to send you to people who will answer your question.
Thank you.
Does anyone know where to find me? Maybe I should write it in the chat. This is me. This is my email address. Feel free to ask me anything you like.
Maybe another follow-up question in that respect. In the past, I've been running programs indeed in parallel, but the tasks as such, they were dependent on each other. So first you had like 800 tasks that need to be completed. This gives you a result, and then from that result on, you divide it again in a smaller number of tasks, and you can continue like that.
Right.
So would that normally be something that Slarm can help you with?
To decrease the number of tasks as you go.
So let's say you know that there is 800 tasks at the beginning, and then from these 800 tasks afterwards, you need to go in this direction. 400 tasks need to be run afterwards. But that can only be done if the 800 tasks are finished. Is that something that Slarm can help you with, or is that something that?
To be honest, again, I don't know if there is anything super smart, but I don't think so. I think that Slarm typically reserves a number and submits a job reserving this number. So what you can do is you can try to write a script that handles the submission script. So for example, it can, submit an 800 CPU job, wait until it finished, and then based on that, submit the next job to the Slarm. So I think if I would be trying to solve this, I would write a kind of babysitter script that would submit jobs on your behalf. So make one level of complexity out of it.
Yeah, I understand. But Slarm doesn't have something that can notify you when the job is ready, or
yes, it can. So well, first of all, in many HPC implementations, they can actually send you an email. Oh, your job is ready. But of course, as far as just having a babysitter script is concerned, it's quite trivial, because in the queue there will always be a job with a certain number, right? And you can always check the queue once in a while, and then once this number disappears from the queue, well, your job is done. The other question is whether it is done because it completed successfully, or it is done because it failed.
Yes.
So then you will need to make your babysitter script a little bit more smart to actually read the output and analyze it a bit.
Yeah, understand.
So I would probably Slarm, somebody, Igor, Slarm, how to queue up a task when another task is finished. Igor, can you comment on that? Or did you just Google that?
I just Googled it, but it's not precisely what Martijn, what Martijn asked. It just in your main submission file, if you need to run, let's say 800, it can call after finishing. So it's not instantly creating a task. It creates task after finishing of the last submitted, after end of execution of the last
of the previous
sequence tasks.
Right. Okay.
So it seems like not like direct solution, but perhaps as a way around, as something.
Right. Jerry, write it down for me, please. This question as well. We have 2 questions so far that I need to get back to.
Yes, I will write them down at the end of the Markdown Hackam day.
Great, thanks. I'll try to come up with a better solution. I personally would write a babysitter script, but maybe there is something already that you could use.
Then I think this sort of wraps it up for today. I want to thank Dennis for giving the presentation. And I'm
Thank you for your attention. I hope that it was not overly boring for people to just listen to me. But Corona, unfortunately, made it impossible for you guys to actually use your own TIEs.
Yeah. So next time we will make sure to actually be here again and to get our hands on the pies and do these kind of computational setups. Probably we will run into different problems then, but then we also know how to actually solve them.
Also, hopefully next time we're trying to organize a workshop, the Delft Blue will be actually up and running. Maybe we could try to scale things up.
That would even be amazing to see the different power, like the performance difference between a Raspberry Pi and a supercomputer. So
and then we by accident discover, because nobody ever tried it before, and by accident discover that Raspberry Pis are faster. That would be funny.
Who knows?
Yeah.
And yeah, I'm personally surprised that within 2 hours we were able to do actual sort of science. I thought we would just be able to compute pi with some digits, but
right, which we did.
which we did, but then even took it further and had more examples. So yeah, to me, it was a very, very nice workshop.
Well, thank you very much. All right. Yeah. Thanks, everyone. Anyone has anything more to say?
Thank you, Dennis, for explaining and also showing all the examples that
No worries.
it's good to relate to at least.
Right.
Yeah.
I'll try to get back to all your questions.
Thank you, everybody. I see Jose is actually turning up now. So hi, Jose.
All right. Hi, Jose. How was your German, Dutch course?
I guess we'll talk about it later. But thank you again for everybody joining us. We'll have more events coming up soon. Please hold on. And from January onwards, as Jerry mentioned, we'll be having regular workshops, not to mention talks and discussions. We'd also hope to share with you what we had developed as part of Open Hardware so far, some of the projects in person that we will also do starting from the new year. So thank you very much and have a great weekend. Bye-bye.
Bye-bye.